I will briefly talk about deep neural network architecture search, which is one of the design tools provided in the Sprint projects. Neural architecture search is able to automatically produce artificial intelligence models. An artificial design task usually requires to process a huge amount of data, develop models capable of extracting information from the data, and these models must be tuned to improve their model accuracy, and also deployed in modules and applications. The main drawbacks of this lifecycle is that they require expertise from AI experts and application experts to produce good results. In fact, intuition and critical use found in the literature not always grant good results for a problem, and the process can be quite time-consuming. And also, the main problem is that not always this expertise is available in the market. What neural architecture search does is automatize this step of architecture engineering. So, basically automatizing the process in which the models are built and improved to reach the best accuracy for the task. The networks found by neural architecture search are often capable of reaching state-of-the-art results that rivals the ones found to handcrafted models. Our work is based on progressive neural architecture search, called POPNAS, which is one of the most endorsed works in the NAS literature. POPNAS defines a search space and starts by training the simplest model in this search space. After the training, a controller network, which is based on STM, is trained on the accuracy results of these networks, and it is used to forecast the accuracy of the expansions of these networks. So, POPNAS basically progressively expands the networks until a target amount of operators is inside each network, and the process repeats cyclically. POPNAS is able to find top accuracy networks, but it suffers from two main drawbacks. The first one is that it only considers accuracy as an optimization target, and the second one is that it doesn't scale well with the amount of data and the amount of networks to train, since the time is not optimized. And therefore, our idea with POPNAS, Pareto-oriented progressive neural architecture search, is to train another surrogate model called time predictor and pair it with the controller to basically predict both the training time and the accuracy of these networks, and build a time accuracy Pareto front on it, so that it is possible to optimize multiple objectives inside the search method, and therefore to choose the trained networks which are optimal regarding the optimization problem. So instead of training only the best networks, it is possible also to find a trade-off between multiple objectives, as shown by the picture, where we have the accuracy and the time to optimize. This work has been published as part of the Gecko conference. To summarize, we transition from handcraft design process, where the deep neural network models are manually defined by experts and application experts, which can possibly stack in local minima, so they must be iteratively and progressively optimized and tuned for the task, and they are prone to bad intuitions, and also it's a very time-consuming process. And we transition, thanks to neural architecture search, to an automatic process which search automatically the deep neural networks models which are the best for the task considered, so the state-of-the-art models, with a good trade-off between accuracy and training time required. Hopefully, this process also requires no human effort, so there is no AI expertise required. Now I'll provide a brief demonstration on how the POPNAS tool works. Here you can see an example of a configuration file used in the POPNAS tool. The JSON is structured in different sections. The most important one is the search space section, which defines for how many blocks the progressive neural architecture search is performed, how many CNNs are trained in each step, max, and the operator set used for the run. Another important section is CNN hyperparameters, which defines all the hyperparameters used during the training of each CNN. The architecture parameter section instead defines the parameters used to build the final architecture from the set encoding. And instead the data section defines some parameters about the input datasets used for the run. For example, here we use the CFAR10 dataset, and we are using only the first 10,000 samples to have a very fast demo run, and we are also using 10% of the samples as validation set. Another important parameter is the POPNAS mode flag, which if set to true, the algorithm basically defines reverse to POPNAS, so it will not use the time predictor, neither the Pareto optimality step. POPNAS tool provides a Docker file to build a container which has installed all the dependencies required for building and compiling the program. Software can be so distributed easily to the final user through the usage of a Docker container. Running POPNAS is very simple. We just need to execute the rumpy script with Python and specify the jflag, which is the path to the configuration file, which is examined before. The algorithm starts by training the empty cell and then all the unique cells with only one block, as you can see here. In later steps, the cells are expanded with additional blocks until the target amount of block is reached. You can see the results of the network's training in the terminal, or you can also see them in the front end. So you can see the configuration, for example the configuration that we used and that we explained before, for GPU, POPNAS mode, 3 epochs, 3 blocks, CFAR10, 10,000 samples. You can see here the training results of each network. You can also zoom and see, for example, a single network, how it performs during the epochs. You can see also an overview of the results of each cell, and for the accuracy, the training time, the parameter swaps, and the plots that are produced from time to time by the algorithm. So some plots will be available quite soon, others will be produced at the end of the algorithm, so they will be generated during the run. With an additional script, it's also possible to produce some summary slides for the plots generated by POPNAS algorithm. Here we'll analyze some results on a CFAR10 dataset of a complete POPNAS run. In the first slide, there is an overview of all the results, the training of the specular monoblocks, so the blocks which have the same operator and the same input, which in this case is -1. -1 input is simply a sequential connection between each cell, so there are no skip connections, and all cells are used in the final architecture. These results are useful for training predictors. Here you can see the overview of the predictor errors for each step of the algorithm. Here instead some slides about the inputs and operator usage in each step of the algorithm, so for each amount of blocks trained, starting from b equal to 2 to b equal to 5, which is the target of the algorithm. In this slide instead there is an overview of the Pareto fronts found by the algorithm in each step. So for example, for b equal to 2, you can see in the green line the predicted Pareto front, so the values predicted by the accuracy and time predictors. Instead, the blue values are the actual values found during the training of these CNNs. You can appreciate that with time, the progressive method allows to find a very accurate Pareto front that resembles the one predicted. In the final slide, instead, there is an overview of the time and accuracy found by each CNN trained during the algorithm. Performing a comparison between POPNAS and PLUS Schmidt over 4 different datasets confirms that POPNAS can perform a run with much less GPU hours, having a top 1 and top 5 networks accuracy which is competitive with PNAS, sometimes lower, sometimes better, depends on the dataset. Also, when training these top 1 cells found on the datasets for an extensive amount of time, reaching convergence, demonstrate that networks found by POPNAS takes much less training time, and instead the accuracy gap is maintaining between the ones found in the search and the one found with this training convergence.